let's recall our context. The context is x naught and y naught are observations, respectively, of the time and displacement for an object rolling down an incline. And we're trying to find the acceleration, which is twice the displacement divided by the square of the time interval. We get these partial derivatives telling us how much the value of the function changes if we move in the x direction, how much it changes if we move a certain distance in the y direction. Remember, this is an acceleration. We want to see how uncertain our acceleration is. So we recall our original data. X naught, y naught was 3.630. Now that was 3.6 seconds, 30 centimeters. And those observations were assumed to have uncertainties of plus or minus 0.4 seconds on the time, plus or minus 2 centimeters on the position. So, we've made the choice to let delta x be negative, which is going to result in a positive change in our acceleration. Delta y, we've chosen to be positive, so x could be plus or minus, delta x could be plus or minus 0.4. We chose minus 0.4. Delta y plus or minus 2. We've chosen plus 2. Positive here, negative here. The delta f is approximately equal to fx delta x plus fy delta y, and this is a straightforward calculation, so I'm just going to point. All we've done here is we've taken the expression for fx and plugged in the values of x naught and y naught. And we obtain this expression and our value of delta x, which is negative 0.4. And we've done the same thing for our fy. Fy is 2 over x squared, so we're going to get 2 over 3.6 squared times delta y, which is plus 2. And the results I've gotten just from a mental calculation, and you can't trust that, so do this yourself. The fx delta x turns out to be about 0.6, the fy delta y about 0.3, giving us a total delta f, a total uncertainty in f of 0.9. Once more, what this means is that for these values, this difference here, the difference between the f of x naught y naught value and the f of x naught plus delta x, y naught plus delta y value is about 0.9. And recalling the larger region, okay, the region that went from x naught, y naught, delta y to the right and to the left, and delta x this way and this way. For that whole region, this is the maximum deviation that we can expect to find. We don't expect the f value to differ from the x naught y naught value, f of x naught y naught, by more than 0.9. For any point in that bigger region, we expect that 0.9 is the maximum possible deviation. Now, had we gone to the opposite corner of our large region, which would be about here on this picture, we would have probably expected a negative 0.9. So we say that f of xy is equal to the f of x naught y naught, this value, plus or minus this delta f. Now we evaluate f at x naught and y naught. Here's our function. We plug our x and y values in, and I think we get something close to 4.6. Again, this is something you should figure out for yourself. There's plenty of evidence coming up that my calculations aren't particularly accurate in this case. So we have 4.6 plus or minus 0.9, telling us that we expect an acceleration of 4.6, but with an uncertainty of 0.9. Our actual acceleration could be then as great as 4.6 plus 0.9, which is 5.5, or 4.6, or as low as 4.6 minus 0.9, which would be 3.7.